Hello everyone, this is Shifa Nizami, Faculty, Department of Physics, Vibrant Academy. Today we shall be taking the topic electricity. In this topic, we shall be taking the entity around which this topic revolves, that is charge. Furthermore, we will be discussing about the effects of this charge depending upon its state, whether it is at rest or it is in motion. Then we shall be discussing about our electric field. Along with electric field, we shall also be discussing about potential. Whenever we speak of the term electric, this term always revolves around one entity known as charge. We all are aware about this quantity, this name charge, but we don't know how to exactly define it. Shall we start with the definition of charge? It is the fundamental intrinsic property of any body due to which we get electric and magnetic effects. Having said that, charge is the fundamental intrinsic property. Intrinsic in the sense it does not depend on anything like mass or speed. Property means anything that is inherent by a body, due to which we get electric and magnetic effects. In this chapter, we'll be dealing with solely electric effects. Okay. When we said that fundamental property of any body, we all know that all the bodies are made up of atoms. Whenever we speak of atoms, in any stable state, we know that our atom has got a nucleus inside it and one electron. The nucleus of the atom consists of neutron and proton. We already know that electrons comprise of a negative charge and proton comprise of a positive charge. In any stable state, for an atom, we say stable state means neutral state of the atom. Whenever atom is in its neutral state, that means number of protons equals to number of electrons. So what happens that we get a body charge? Whenever two bodies rub against each other, what happens? Some of the electrons jump from this body to this body. Hence, what we get? Number of electrons in this body are less than the number of protons. This means that as a whole, this body has got positive charge. Now, what about negative charge? When we rub these two bodies, the electrons that got jumped from this one came in this body. When the electrons came in this body, that means number of electrons in this body is greater than the number of protons. As a sole result, we say that this body becomes negatively charged. This is the whole story for a body to get charged. Now that we have two bodies which are charged, one is called positively charged body, another one is called negatively charged body. So shall we be taking some properties of these charged bodies? Or to be simply put, we shall be taking properties of charges. Remember, all of these properties we have already studied in our 8th standard. We shall be just revising these properties so that we shall smoothly go onward to our further topics. First property. Remember, we have studied in 8th standard that like charges repel each other and unlike charges attract each other. This forms your first property. Like charges repel each other and unlike charges attract each other. One thing to note in this first property is that whenever we say unlike charges mean not only positive and negative but also positive and neutral or negative and neutral. Like charges repel each other. You must have done at your home parties. Whenever we rub two balloons from our hair and we bring those two balloons near to each other, they get repelled from each other. Whenever balloons are rubbed with hair, both the balloons attain the same charge. And whenever we bring them closer, what are they doing? They are repelling each other. Now, take one balloon and try to stick it to the wall. It easily happens. Why? Because now that balloon has got one charge and your wall is neutral. So, a positive charge and a neutral body, or a negative charge and a neutral body, also attract each other. Also at the same time, when you have rubbed the balloon with your hairs, after some time when you again bring that balloon towards your hair, what happens? Hairs get stuck to that balloon. That means some of the electrons got jumped from your hair and the balloon attained those electrons. When the balloons attained those electrons, balloon got negatively charged, your hair got positively charged. Positive and negative again attract each other. Alright. Our second property. Since everything is made up of atoms, and in all the above examples that we have discussed before, what we did? We have jumped electrons from one body to another body. That means our basic fundamental charge particle is what? Electron. This is our second property. Fundamental charge particle is electron. So there must be some charge on one electron. Sure it is. Charge on one electron equals to 1.6 into 10 raised to power minus 19 coulombs. Coulomb being the SI unit of our charge. Since we are saying charge on one electron is just this much, that means there must be many number of electrons in 1 coulomb charge. Let's see how many electrons are comprised in 1 coulomb charge. Can we rewrite it as 1.6 into 10 raised to power minus 19 coulomb is on 1 electron. Then using simple unitary method, 1 coulomb will have 1 upon 1.6 into 10 raised to power minus 19 electrons. When you further solve this equation, what will get? This equals to 6.25 into 10 raised to power 18 electrons. This figure is what we need to mug up. Always remember the value of 1 upon 1.6 into 10 raised to power minus 19 is 6.25 into 10 raised to power 18. Okay, these are the two properties. Let's speak about our further properties. Property number 3. This property revolves around basic nature of our quantities. Have you ever heard anybody saying, भाई यार आधा इलेक्ट्रॉन दे दे मेरा तो उसी में काम चल जाएगा? It never happens. Why? Because charge is always quantized. Since we are saying this term quantized in the sense, whenever one body gives out electrons, it gives out electrons in whole numbers, either 0 or 1 or 2 or 3 or 4. Alright? That means charge. We'll be denoting total charge on a body by the letter small q. Small q equals to n into E. This E being the charge on one electron, and n is nothing but your whole number. 0, 1, 2, 3, likewise. Since only electrons are going to be transferred, that's why, and since we cannot transfer fraction number of electrons, that's why we say that charge is always quantized, or our third property is known as quantization of charge. Okay. Further, coming to our fourth property. Whenever this body gives out electrons and this body is catching those electrons, always remember that the total charge of this whole system in the sense this system is comprising of both of these bodies. Total charge on the whole system is always conserved, which is nothing but our fourth property, that charge is always conserved for a system. Why have I written for a system? Because it is so obvious that when one body is giving out electron, charge on that body is not conserved. And when another body is taking that electron, charge on that another body is also not conserved. But as a whole, number of electrons giving out from this body and taking into this body are conserved. Whenever we say this term conserved, conserved means it can neither be created nor be destroyed. But does this statement ring a bell? Yes, exactly what we say in case of energy. It can neither be created nor be destroyed, but can be transferred from one body to another. These were the four major properties of charges, but along with it, we have got one more property of charge. And that property is nothing but telling the basic nature of charge. Charge is invariant and scalar. Yes, these both are the new terms. Invariant. Variant means anything that changes, and invariant means something which is constant or something which does not change. But with what factor? Whenever we say that charge is invariant, that means that charge never changes with speed. Here the sole factor driving this term is speed. And we are also saying charge is scalar. You remember we have already studied scalar and vector quantities in our lower classes. Scalar quantity means anything that has got value and which follows normal mathematical algebra. If one body has got, let's suppose body 1 has got plus 3 coulomb charge, body 2 has got minus 2 coulomb charge. And when I ask you, what is the net charge on the whole system? So net charge on the system would be nothing but scalar addition of these two values, that is plus 3 plus minus 2, which is equal to, that is plus 1 coulomb charge. So our system comprising of body 1 plus 3 coulomb charge and body 2 minus 2 coulomb charge has a net charge of plus 1 coulomb. Alright. This is it in the properties of charges. Now we shall be discussing about the effects based on the state of charges. Since we are talking about the effects based on the state of charges, let us discuss about the state of charges. Charges could be in two states. One, rest. Another one, motion. Motion could be either uniform or accelerated. Whenever charges are at rest, they produce electric field around it. Whenever charges are in motion, they produce electric field along with magnetic field. Around them. This whole effect is read in a branch of physics known as electrostatics. Electro again means related to charge and statics means something which is at rest. This effect is read in another part of physics called as current electricity. In this chapter, we shall be solely focusing on current electricity, but before that, let us discuss what does this field word mean and what is the significance of the word electric and magnetic. Let's discuss it one by one. In 9th standard, we have already studied the chapter gravitation. Let us take that analogy from gravitation. Just like gravitation, there is a force which depends on the masses of the body and the distance at which those two bodies are kept. This force is always attractive in nature and depend on product of the masses and inversely proportional to the square of the distance between them. Small g means gravitation force. When we remove this proportionality sign, we get a constant of proportionality, universal gravitation constant in case of gravitation. And this universal gravitation constant does not depend on any medium or any value. It remains constant throughout the universe, throughout the places, throughout the bodies. Okay. This was when we talked about the masses and the bodies. When we speak of the charges in the bodies, we have got one force known as Coulomb's force. Now, this Coulomb's force, just like the gravitation force, depends on the product of the charges and inversely proportional to the square of the distance between them. Let's suppose these are two charges Q1, Q2 separated by a distance r. So there is a force which is experienced in between these two charges, and this force is directly proportional to the product of these two charges and inversely proportional to the square of the distance between them. When we remove this proportionality sign, what we will have? We will again have a constant, but unlike gravitation force, this constant depends on the medium. In gravitation force, this constant was known as universal gravitation constant, but in Coulomb's force, this constant is known as Coulomb's constant, and its value is equal to 9 into 10 raised to power 9 Newton meter square per Coulomb square in vacuum. According to your medium, be it air, water, kerosene, anything, this value of K changes. Gravitation force. Gravitation force, when we talk about the nature of the forces, gravitation force is always attractive in nature. But your Coulomb's force, remember the first property of charges, like charges repel each other and unlike charges attract each other. This Coulomb's force could be either attractive if the charges are unlike, or it could be repulsive if the charges are like. If this is negative negative or positive positive, this Coulomb's force will be repulsive in nature. If this is positive, this is negative, or this is negative, this is positive, this Coulomb's force will be attractive in nature. Okay. Now that we know two charges have got some force known as Coulomb's force in between them, so definitely when we leave one charge in space, it would create some field around it, in which whenever this second charge is brought, this second charge will experience some force, right? So let us discuss what this field is called. Basically, in case of Coulomb's force, this field is called electric field. Again, electric word means due to a charge. Let's suppose I have kept this Q1 charge. This Q1 charge will have some field around it. In this field, whenever another charge is brought, that charge will experience a force. Let us take it with some analogy. We all watch sports. In fact, many of us play so many sports, right? Let us take an example of WWE ring. Okay. In WWE ring, what happens? This is your ring. This charge, let's say this is John Cena. John Cena is inside this ring. Okay. John Cena is inside this ring. That means whosoever comes inside the ring will have to face the wrath of John Cena. Let's suppose there is another wrestler. Let's say Hunter over here. Here, what is important is the boundary. As far as Hunter is outside this boundary, John Cena will do nothing, right? But the moment Hunter steps onto this boundary, what will happen? Time begins, right? John Cena will play his part on Hunter. Exactly, he will fight him. Just like this case, our charge has made its boundary. The moment another charge is brought onto this boundary or inside this boundary, this another charge will be fought by this charge who has set its own boundary. And this boundary and the region inside this boundary, this is known as the electric field of this inside charge. So, having said that, can we now discuss the definition of electric field? Electric field is nothing but a region of space around any charge in which when an external charge is brought inside, what happens when this external charge is brought inside? That external charge experiences a force which is actually Coulomb's force. It experiences a force due to that inside charge. This is basically our electric field. Nothing but a region of space around any charge, in which when another charge is brought inside, that another charge experiences a force due to this charge. Okay? So, we don't know what this external charge could be. Our Coulomb's force was what? K Q1 Q2 upon R square. We don't know which external charge could it be, right? So our electric field is nothing but solely due to this inside charge, that is our Coulomb's force divided by that external charge. SI unit of force is Newton, SI unit of charge is Coulomb. So SI unit of our electric field is Newton per Coulomb. Now, what do you mean by potential? Potential means capacity of anything, right? And since we are talking about the charge, that means capacity of any charge. But capacity in what sense, right? We have discussed about electric field of this charge. Capacity of this charge would be nothing but work done by this charge in bringing that external charge inside its field without changing its kinetic energy. Alright, this is the potential of this charge. Okay, when I speak about my potential would be what? Taking lectures, right? Potential of John Cena would be what? To fight till the time ends. So likewise, potential of this charge would be what? In the sense of field. potential of this charge would be to bring any external charge inside the field to any point, let's say to a point, without changing its kinetic energy. That means potential in broad sense is nothing but work done, right? Work done per unit charge. So our potential is nothing but it is the work done in bringing a unit positive charge inside the electric field from infinity to any point. Okay. Since I have said it is the work done in bringing a unit positive charge. A unit positive charge means value of this charge is nothing but 1 coulomb. Inside the electric field from infinity to any point. The point to ponder here is infinity. What is the sense of infinity? Okay. Whenever this word is struck in our mind, we say infinity means a point beyond which we cannot see. But that infinity is in terms of vision. If I tell you about my infinity point would be that pen. Why? Because my hand cannot reach that pen, right? Any point beyond my reach, a point just beyond my reach would be infinity for me. Just like that. What would be the infinity for this charge? Just like the infinity for John Cena would be the boundary of that field, the boundary of that ring, right? In the same manner, the infinity for this Q1 charge would be this boundary, beyond which our unit positive charge is kept, right? Now, what this charge will be doing? This charge will be bringing this unit positive charge from infinity to a point inside this field. Exactly. Infinity to any point. Here, this point is A. So, potential will be referring potential by capital V. Potential of point A is nothing but work done divided by this unit positive charge. So, what about the potential difference? Potential at point A is work done in bringing this unit positive charge to point A divided by that unit positive charge. Let's suppose there is another point B. Potential difference between A and B. Potential of point B would be what? VB equals to work done in bringing that unit positive charge to point B from infinity divided by that unit positive charge. So, potential difference between point A and between point B would be nothing but delta V, which is VA minus VB WA minus WB divided by Q. This was the broad sense of potential difference. Potential difference is nothing but work done in bringing a unit positive charge from point A to point B. The SI unit of potential is volt. Similarly, SI unit of potential difference will be volts, because when we subtract mangoes from mangoes, we will never going to get chikus, right? In the same manner, whenever we subtract volt from volt, we will be getting volts only. So, shall we discuss a question related to it? After that, we will just conclude our today's lecture. And in the next lecture, we will be taking further part. We will be starting from the topic current. Alright? Let's take a question. Let's suppose it is given that work done in bringing a plus 4 coulomb charge from infinity to a point A is 96 joules. Also, it is known that work done in bringing the same charge from infinity to point B is 24 joules. You need to find out what is the individual potential of points A and points B . This is your first part. Your second part asks, what is the potential difference between points A and B? Okay. Everything is given in the question. Work done in bringing a plus 4 coulomb charge from infinity to a point A is 96 joules. Which charge are we bringing? Plus 4 coulomb to point A, remember. Also, it is known that work done in bringing the same charge from infinity to which point? B is what? 24 joules. What is the individual potentials of points A and B? Potential of point A would be what? WA upon Q. 96 upon 4, right? Potential of point B would be what? WB upon Q. 24 upon 4. And then your second part, what is the potential difference between A and B? Potential difference between A and B would be what? VA minus VB, right? Alright. Q is given to be 4 coulomb. WA is given to be 96 joules. WB is given to be 24 joules. From Q and WA, we will have our first part. (24 volts). From WB and Q, we will be having our next part. that is potential of point B. Six volt. For the second part, potential difference between A and B. VA minus VB, 24 minus 6. This is how we are going to solve next our questions. Okay? Alright. So, this is for our today's lecture. We shall be concluding it here. In the next lecture, we'll be taking electric circuit, we'll be taking current, and we'll be taking a few of the other properties known as resistance. Okay? That be all for today. Thank you.